Dr. Silly and Bobby Sponge are here. Last week, nobody came. This week, 2 people came. Whether this constitutes a significant improvement depends entirely on how you define the null hypothesis. We will get to that. You reported p equals 0.03. You called it significant. You wrote statistically significant difference in the results section. You moved on. The problem is that p equals 0.03 does not mean your result is real. It does not mean the effect is large. It does not mean the experiment worked. It means one specific thing, and most people reporting it do not know what that thing is.
Wait, p equals 0.03 doesn't mean it worked?
No.
But everyone reports it like it means it worked.
Yes, that is the problem. The p-value is the most widely reported statistic in biology. It is probably the most widely misunderstood. Those two facts are connected. Statistical significance is a noise floor. You decide where the floor is, you run the experiment. If the result is loud enough to cross the floor, you call it signal. If it doesn't cross, you don't. The floor doesn't know what you measured. It only knows whether you crossed it.
That doesn't sound like statistics. That sounds like a microphone.
It is the same principle. If you have been treating p less than 0.05 as evidence that a result is real, subscribe. There is more to correct. The method begins with a position called the null hypothesis. The null hypothesis says there is nothing here, no effect, no difference, no signal, pure noise. You do not believe the null hypothesis is true. You are testing whether your data is consistent with it.
To be precise, you're assuming it's true for the purpose of the calculation. You're not claiming it's true.
Correct. You inhabit the null hypothesis temporarily in order to calculate a probability. You do not endorse it. You collect data. You calculate a test statistic, a number that summarizes how far your data is from what the null hypothesis predicts. For a t-test, that is the t-statistic. For a chi-square test, chi-squared. The formula depends on the test. The logic is the same. How far is this result from silence? Then you ask a specific question. If the null hypothesis were true, if this were pure noise, how often would a result this extreme or more extreme occur just by chance? That probability is the p-value. Formally, p equals the probability of observing data at least as extreme as yours, given that the null hypothesis is true. P is calculated under assumed silence.
At least as extreme? You mean in both directions for a two-tailed test, or just one?
Depends on the test. A two-tailed test shades both ends of the null distribution. A one-tailed test shades only one. The choice must be made before looking at the data. Making it after is not permitted.
And the p-value is p of data given h naught, not p of h naught given data.
Correct. Those are different calculations. The second one is what people think they are reading. It is not what the p-value says. You compare p to a threshold. That threshold is alpha. Convention places alpha at 0.05.
Wait, someone just picked 0.05 and everyone went with it?
Ronald Fisher suggested it as a convenient level in 1925. It has stayed at 0.05.
That's it? That's the whole reason?
Conventions are stable. 0.05 is not derived from biology. It is not derived from physics. It is a round number that someone wrote down and everyone else repeated. If p falls below alpha, you reject the null hypothesis. You declare that the result crossed the floor. That is all that happened. The floor didn't move. The data was loud enough to cross it. What you are not calculating, the probability that the null hypothesis is true, the probability that your result will replicate, whether the effect is biologically meaningful. The p-value is silent on all three. It answers only the one question it was designed to answer, and that question is not the one most people think they are asking.
So what is the p-value actually answering, stated precisely?
It answers, assuming there is no effect, how surprising is this data? That is the complete answer. Nothing else is in the calculation. A correctly reported result includes the p-value, an effect size, a confidence interval, and the sample size. Effect size is the volume of the signal, Cohen's d for comparing means, r for correlations, and odds ratio for binary outcomes. Effect size tells you how loud the crossing was. The p-value only tells you that it crossed.
So if a paper just has a p-value and nothing else, it's incomplete?
Many published results are incomplete in this way. A 3% difference and a 300% difference can both produce p equals 0.04. The p-value does not distinguish them. The effect size does. A badly reported result looks like this. P equals 0.04, n equals 6. No effect size, no confidence interval. You know the data crossed the floor. You have no idea what crossed it or by how much. You cannot evaluate whether it matters. If you have been reporting p-values without effect sizes, you have been answering the wrong question and leaving the right one unanswered. The right question is, how large is this effect? And how precisely have I estimated it? The p-value is a side calculation on the way to answering that. It became the main answer. That is the problem. P equals 0.049 and P equals 0.051 are the same result. The floor made them look different. The biology did not.
The threshold creates a false discontinuity in a continuous measure.
Yes. The p-value is not the probability that the null hypothesis is true. P of data given hypothesis is not the same as P of hypothesis given data. They are different calculations that require different inputs. Confusing them is called the prosecutor's fallacy. It appears in published biology papers regularly enough that it has its own literature.
P of H naught given data is what Bayesian inference calculates. That requires a prior.
Yes, we will come back to that. Alpha is not a property of the data. You set it before you look at the data. Alpha equals 0.05 means you accept a 5% rate of crossing the floor when there is no signal. In a silent room, 5% of experiments will produce a significant result.
So 1 in 20 experiments is just wrong by design.
Under the null hypothesis, yes, that is the accepted false positive rate. You chose it. Multiple testing scale is the problem. If you measure 200 proteins and test each at alpha equals 0.05, you expect 10 false positives by chance alone. If you do not correct for this, Bonferroni, Benjamini-Hochberg, false discovery rate, those 10 crossings are treated as findings. They are not findings. They are the expected output of 200 quiet tests. Genomics encountered this when association studies started producing thousands of spurious hits. The correction is not optional. It is arithmetic.
Oh no.
The correction is embarrassing. You ran many tests. Of course, some of them passed. You did not discover anything by default. Power is the probability that your test will cross the floor when a real signal exists. An underpowered study fails to cross the floor, not because there is no signal, but because the signal was not loud enough relative to where you placed the floor. An underpowered study that returns p greater than 0.05 does not demonstrate that there is no effect.
Absence of significance is not evidence of absence.
Absence of crossing is not absence of signal. Yes, those are different statements. Reporting them as equivalent is an error that appears frequently in negative result papers. Statistical significance and biological significance are not the same thing. A large enough sample makes any non-zero effect statistically significant. An N of 10,000 will give you P less than 0.001 for a 0.2% difference in cell viability. That difference has crossed the floor. It has not become worth studying.
Wait. So a huge study can make a completely useless difference look significant?
Yes. The floor does not scale with importance. Sample size and effect size together determine whether you cross. The floor only knows about crossing. P-hacking works because the threshold is fixed and the number of attempts is not. Keep collecting data until you cross. Keep running subgroup analyses until one crosses. Keep adjusting the model until the coefficient crosses. You will eventually cross. The p-value assumes one planned test on a fixed dataset.
Does checking the p-value partway through data collection and then stopping early count?
Yes, that is called optional stopping. The p-value assumes the sample size was determined before data collection began. Stopping when you cross inflates the false positive rate beyond your stated alpha. The floor shifts without you knowing. Publication bias means the published literature is a selected sample of experiments that crossed the floor. Experiments that did not cross are less likely to be submitted, accepted, or published. The result is a record bias toward crossing.
So the literature is a biased sample of all experiments run.
Yes, the file drawer problem. The experiments that didn't cross are in file drawers. The ones that did are in journals. A field that publishes only crossings will have a literature full of crossings that do not replicate. In direct replication attempts, roughly 50% of published psychology results did not replicate. The figure in preclinical biomedical research is similar and possibly higher.
50%?
A consistent feature of non-replicating results is small sample sizes, effect sizes that are implausibly large, and p-values clustered just below 0.05. This pattern has a shape. The shape is consistent with floors crossed by noise being reported as signal. It is mildly instructive that the most universally reported statistic in biology is answering a question that nobody is actually asking. Nobody wants to know the probability of data under an assumed null. They want to know whether the effect is real and how large it is. The p-value answers neither. It has been used as a proxy for both for a century. The tools to answer the right questions exist. Pre-registration fixes the number of planned tests before data collection, so the floor means what it is supposed to mean. Effect sizes and confidence intervals report what you actually found. Bayesian methods return the probability of the hypothesis given the data, the calculation people believe the p-value is performing.
Why doesn't everyone just use Bayesian then?
It requires specifying your prior beliefs about the hypothesis before seeing the data. That is uncomfortable. It makes the subjectivity explicit.
as opposed to hiding the subjectivity inside the choice of alpha and test.
Yes, frequentist methods are not less subjective. The subjectivity is just less visible. The test asks whether the null hypothesis can explain your data. Nobody asked whether